All right, y'all. It is 10 o'clock. Just to be prompt with time. I'm gonna go ahead and start it. I'll do my best. I can't really see who's going in because my computer was not wanting to work with Zoom this morning. So I apologize ahead of time if I miss any questions. Just chime in with your microphone to let me know though if you have questions. I cannot see the chat. Can everyone hear me okay? I guess that's probably the first thing I should check. Is my sound going through clearly?
Yeah, we can hear you.
All right. I got it recording though. But what I want to do today was just kind of continue where we left off last week, looking at functions and minimum of maximums as far as increasing, decreasing concavity. Today, though, we want to look at like some different application problems we're dealing with maximizing and minimizing. So go ahead and write down this problem. I'll give you a couple seconds and then we'll go ahead and get started. All right, so sorry about that. Going through this problem though here, what you see is you have this rancher wants to enclose two rectangular areas near a river. Thankfully, they gave us a little picture with this. So we have two areas that they want to make, one for sheep and one for cattle. They have 240 yards of fencing to use, and they want to know what is the largest total area that can be enclosed. Okay. So what you want to make sure you see here, though, that this is very specific, that we have 4 pieces of fencing that we need to account for because the river is going to be the other backside of that. Okay. So that's what we want to work on. But now keep in mind, this is where we're going to start jumping into things that's focusing on how to maximize or minimize something. So like in this instance, the geometry is going to help us because we're talking about rectangles, but we want to have the maximum amount of area where the sheep and cattle can be kept, given the fact that all we have is 240 yards of fencing. Okay. Now, what you have to do is make sure you're careful when you're dealing with these problems to go in and make sure to identify all the pieces that you're working with. So one thing to look at here is that we're going to have 2 areas that we want to keep in mind here. We're going to have the area 1 and area 2. Now, when we look at that area, each of these are going to be found by doing x times length times width, I should say, for those 2 little rectangles that we have. Now, what I think we're safe to assume is that we want to have equal spacing so that this right here, whatever this length is here, we'll just call it y. This is going to be y over 2, and this is going to be y over 2. So I think we can confidently say, hey, 2 areas, or both areas need to be of equal size, which will be nice here because what happens is when we deal with this, we'll say area 1 will equal x times the y over 2, and then area 2 will equal x times y over 2. But when you add those together, right, well, those are both the same thing. So you could just write 2 times x times y over 2. Well, guess what? That's just x times y. All right, if we're assuming that the 2 areas are the same, we're just looking for the entire area at one time, which is what's nice about it. Okay, but you can see here, that's on the assumption that we want both of them to be exactly the same size here. Okay. So just kind of showing that, make sure you remember the area of a rectangle. Volumes will be something we look at today. So here we would say, hey, the area we're interested in maximizing is just length times width, x times y. Now, the other part that we have to take in account here, though, is where the fence is at, right? So when we start dealing with these maximizing problems, you're going to have multiple pieces. Think about the business application. We talked about costs. We talked about revenue and profit. There's going to be different things here that are important. You always want to make sure to go in and see, hey, what are all the pieces I need and how can I begin to put them together? Well, an important piece that we have here is there's only 240 yards of fencing. And the fencing here is going to make up the outer wall and the dividing wall. Well, what that is a perimeter. And the nice thing about the perimeter, if we stick with each of these being X as is shown here, the perimeter that we're going to be building with this is going to be 3 times X because we have X plus X plus X plus Y. All right, that's just us saying, hey, I got 1, 2, 3 fences that are going to be length of X, and then the long front fence, we're just calling Y. I put the Y there ourselves from the beginning. Okay. Now, the nice thing about this equation, though, is we actually know the perimeter. Okay, that's definitely an important part that you want to take from that. Hey, that is something I know. And the reason we want to do that is right now, we had an equation with 3 variables that we didn't know, and a second one that had 3 variables that we didn't know, but actually, we did know one of them. So now this one only has X and Y. All right, and the reason we like having these 2 equations is because you can then take one of the equations and use it to substitute. All right, so that's what we're going to start working on now. Is there any questions with where I'm getting these from, though, as far as the area and the perimeter equations?
Oh, I'm sorry. How did you get to 3 again?
How many fences of length X do you see?
Okay.
That's where we're like, hey, 1, 2, 3. And the idea there is like this is the outer fence that's making the fenced in areas, right? So that's
Right.
where these X's come from. But they want it to be one side for sheep and one side for cattle. So that's where the third one comes in, is the fact that, hey, this is going to split that area into 2 separate areas.
Okay, I got you.
All right. Now, getting to these formulas is definitely an important part, right? So we have our area. I'm actually going to erase this other one, though, because we can begin to focus on this one, right? Now, this is the one that we're working with because we want to go find the largest total area that can be enclosed, right? So this is the one we want to work with. So what I'm going to do is I'm going to take our perimeter one and I'm going to solve for Y. Now, you could solve for X or Y. It doesn't matter. The reason I'm choosing Y right now is because it's just one Y where X had 3 of them. It just makes it easier to say, hey, if I subtract 3X from both sides, we'll have 240 minus 3X equals Y. And all of a sudden now Y is completely by itself. The reason we like this, though, is we can now take this equation we have and plug it into our area. So we're going to take this Y value that we just found, we're going to plug it in here. And that's going to help us eliminate one of the variables. So now we'll have A equal to X times, and I'm putting parentheses because it's no longer Y, 240 minus 3X. All right. Now, these are 2 different equations we use, but since they both shared X and Y, this is what allows us to plug in where the Y was. All right. That's really nice, though, because you went from an equation that had 2 different variables, right, to just one. And you could actually go in and do stuff like simplify now. All right. You have a quadratic you're working with. Now, the question becomes, I did all that so that I can have the area formula with one variable, but how do we actually go back to the maximize? All right. Well, the maximizing part comes in where we talk about the first derivative and second derivative, right? So what we want to do is take this function that we just found that was now just in terms of X, and let's go find the derivatives of it, right? So A prime So we have the derivative of our linear term and the derivative of our constant term. All right. That's going to help us though, because this is going to allow us then to say, hey, what are some critical points we're looking at? So when does a prime equal 0? That first derivative. And when we set that equal to 0, that's a linear equation. That's kind of nice. Just add a 6 to both sides. Then when we divide by 6, we find that x should be 40. And in this case, make sure you see here, we're looking at yards. So that's an important value. Now, if you wanted to, you could also go do the second derivative, but what you're going to see here is the second derivative is just going to confirm that it's a maximum value. If you look at the second derivative here, it'd be just -6. That means no matter what point we pick, no matter what x value or y value we pick, it's going to be concave down, right? So at this particular critical point, our function has this point here and is doing something like this. So we know, hey, this is definitely a maximum value. Okay. And being it's a quadratic, we can bring in those common terms that we've used like vertex, where we know this isn't just any maximum. This is the absolute maximum value we can have for this particular situation. Okay. Now be careful here though. That gave me x, right? So we know that what we want to use here for each of these x's is 40 yards. But the question that it wanted us to answer, what is the largest area that can be enclosed? So we can't stop there. We have to make sure to go finish the problem. All right, so now that we have x, we can go find y. Well, that's where we can go back to our original equations to help us with, okay? But hopefully you'll see here, this is the one you definitely want to focus on still, because it was solved for y, and on the other side, all we had was the x value, okay? So are there any questions where I'm getting the x from though, before we use it to get y? All right, so keep in mind here, this is a critical point from the first derivative that helped us know that it was a maximum value. You didn't necessarily need the second derivative. That just confirms, though, that this was concave down, so it definitely is a max. Now, keep what as I said before here, we need now take this value and go back to the second equation, right, that we got from the perimeter, and plug in the x value we found. So I'm not using x here now. I'm plugging in the value that we found. And what you're going to see here is that when you do that work, you're going to get 240 minus 120. So y should be 120. We now know that the length of this front wall we want to use is 120 yards. All right. So if they ever ask for like the dimensions, well, the outside dimension would be 40 yards by 120 yards. Just make sure you remember here that when I look at an individual one, if we're assuming they're equal size, that would be 40 and 60, right? So always read the problem though for what they want. That's an important part. And you'll see with some of these, the way they ask the question is definitely going to determine the work you do, which isn't new, right? We've seen this on all the application problems we work with, but it's just always something you want to remind yourself. Now, what they wanted us to do though was to take this now and go find what the maximum area is. So just make sure you see here, now that we have both of them, we can go do, hey, what's 40 times 120? So with that in place, we get what? 4,800 square yards. Or yards squared, if that's the way you want to do it. Either of those would be fine. Any questions or concerns here with this one? All right, so the just kind of conclude this problem before we look at another one. Just make sure you look at the fact that they wanted you to use the area, right? But the area by itself, we wouldn't have had enough information to work with. That's where the perimeter becomes helpful, right? The perimeter allowed me to get to a place where the area is now usable. And oftentimes what you're seeing is, let's make sure I only have one variable in the equation I'm trying to focus on, okay? But what you'll see there is once we were able to do that, my area formula now only had it in terms of X, right? These little short sides. And that's what allowed us to jump into the derivative, specifically the first derivative, and find that critical point. Those critical points are definitely where we're looking for as far as minimizing or maximizing. So here was a maximization problem because of what we were looking for, right? We wanted the largest area possible. Typically, you should hope that the concavity agrees with what you're trying to find. So that was the only reason I did this, was just to show agreement, okay? But you'll see here, like I said, the overall dimensions were given by the 40 and the 120, but what they wanted was this 4,800. Just make sure you, again, watch your units. It should be square yards, okay? Now, the next one I have here is one that's dealing with profit. And what you're going to find here, again, I have a situation where they're going to give us some different functions. The previous one, we had to build the functions from geometry, right? So we'll kind of keep in mind some basic geometry stuff. But here they give us the functions. But make sure you're paying attention to the fact that they give you R of X and C of X. These situations mean that, hey, they're giving me the revenue and the cost. All right. That's the important part here. They didn't give us the profit, but that's what they want me to find, is the maximum profit. All right. Now, what you're going to see as well is they don't want me to do one thing. They want us to find the maximum profit and the number of units that must be produced. So make sure you see that word "and" here as you're going to solve this. So we have to, this is where they want both perspectives. So what do we do to find the, what am I trying to say? The profit. Okay. It's one things that we've worked on quite a bit. So I gave it to you on one test, but moving forward, we just need to remember, hey, the profit's going to be whatever revenue we have minus the cost it took to get there. Okay. So when we deal with this, we're going to take our two functions and do some subtraction. They both already have the same variables, which is nice. So we can go in and just jump into what it's asking us to do. Now, be careful here, though, as I mentioned, both of these were given to me as, I probably should have wrote that, the revenue function, R of X, and the cost function, C of X. You'll see in a second, that's not always going to be given to you directly. You might have to do a step or two before you get to these functions. So be careful to read what you got. So here we have our profit. Just remember, subtract them, but also highlight the fact to yourself that I put parentheses on purpose because we need to subtract every term here. That's definitely one thing we have to be careful of. It's easy to accidentally overlook, and we don't want to do that in this situation. Well, you'll see there, I'll change all those signs in my cost function, and then I can combine like terms. And I'll get negative x cubed plus x squared plus 5x, and then minus 1. I'm getting that from combining these two and these two. You'll see here, these just kind of drop down. Now that's our profit function, right? But we don't want just anything from the profit function, right? We want to maximize it. So what do we need to do to the profit function? Anytime you see the word max, or it might be trying to minimize the cost, it doesn't have to maximize profit. You might want to minimize cost, right? So keep that in mind. There's different things here that can start pulling from this. We need to go down here and differentiate this function. Okay, so are there any concerns with where I'm getting this function from before we go into that next step? All right, so clearing up some room for myself here. Keep in mind the subtraction is what has got us here, okay? To find the derivative of this, so the nice thing is it's just taking each term as we saw before, so dealing with that power rule. It's very important that we're going back over our derivative rules. Go back to your old test and correct your derivative mistakes. It's very important moving forward. That's everything we're doing is dealing with that. But you'll see here, I brought down the 3, subtract by 1, brought down the 2 and took 1 away. And then here it just left a 5. And then any constant term goes to 0. All right, and as we said before, this is where we're now able to go find the maximum values. This is the critical points though. So make sure you see here, this is where I'm taking the derivative and setting it equal to 0 to find critical points. All right, they could be minimum or maximums, right? One thing I would point out too with this is just make sure you understand that these are functions we're working with from an algebra perspective. So the algebra is going to give us 2 solutions in this case, right? Because we have an x squared. Make sure you ignore stuff that doesn't make sense, right? We're not going to produce a negative number of units, right? So if you get a negative solution, just be like, whatever, I don't need that. I'm focused on the positive one, right? If you don't get any positive solutions, make sure you kind of question, all right, let me double check my work. Because like if you mess up one sign here, going from the revenue and the cost and that subtraction, and you don't get the correct signs with these, it might affect what you're trying to do here. So it's very important that we're careful, okay? So with that said, let's take this and set it equal to 0. That's going to give us negative 3x squared minus 2x minus 5 equal to 0. I pulled out a negative just to make it a little bit nicer to work with. What you could find is you just divide everything by negative, but this goes to one of those quadratics we need to factor, right? So if you need to, go back to your AC method, whatever you're comfortable with. If you choose to use a quadratic formula, there's nothing wrong with that, but what you're going to find here is it is factorable. We can use negative 5 times 3 and negative 5 plus 3, okay? What that'll give us then is negative out in front, and then I'll have a 3x, an x, a 5, and a 1. And I want it to be negative 5 and positive 3. Make sure you're going over whatever way is comfortable for you, though. Like I said, if you're comfortable factoring, make sure you're paying attention, reviewing that as you go. If it's quadratic formula, make sure you do that as well. The nice thing about factoring is, hey, I can get to my solutions with relative ease because I'm going to subtract a 1 from both sides. I'm going to add a 5 to both sides. So that's where the negative and the positive number comes from. Here, though, we have to divide by 3. That's why we have a fraction. But remember, as I just stated, we don't need this. It's negative. Okay. So are there any concerns where I'm getting the 5/3 from?
Yeah, can you show it one more time where you got the 5/3 from?
Are you good with the factors, though, where I got that from?
Yes, sir.
Yeah, so make sure you remember there then, I took the factor and set it equal to 0. So you add the 5 to both sides. And then when you get there, that's where you're going to then divide both sides by the 3. So that's where that came from. Taking our factors, setting them equal to 0. So add the 5 to both sides, then divide by 3, and that's where we got that, okay? And if there's something in this situation where you just automatically jump into the quadratic formula, just make sure you go practice that and you get the same. Remember, there was 2 answers here. We crossed this one out, though, because it was a negative one. We don't want the negative one, okay? Now, what you're going to find here is we found one of our answers, right? 5/3, okay, is going to be the number of units that must be produced. It's not the profits, the number of units. And you saw here, it's in thousands. So 5/3 itself, all right, get rid of the negative ones. We don't need it. 5/3 itself is what, 1.66, and keeps on going forever, but I'm just going to stop there at the thousands place, because once you multiply it by 1,000, that'll be 1,676 units that would be produced to get the maximum profit. Now, the thing that you have to remember to do now, though, is take this value and plug it in. So we want to go find P, not P prime, right? But P of the 5/3. And you could just plug in 1,667 as well. But make sure you have a calculator and you're comfortable with it, especially because we have the the x cubed, sorry, with this one. Now, the exact answer that if you plug in the 5/3 is 148 over 27, but we're not interested in that. We want to say that this is about 5.481, right? Because again, we're in thousands of dollars. So with that many units, the maximum profit, the maximized profit, I should say, would be $5,000, $5,481. If you wanted cents, whatever you could. You'll see this is a repeating decimal, but I think we're good here. Just make sure, again, as you saw, I plugged this back into here. Was there a question? Any questions with that? All right, then just to recap, then make sure you see here, they wanted me to maximize the profit in the number of units produced to get that, right? But they gave me the revenue and cost functions. So the first thing you had to go do was find the profit function by doing the revenue minus the cost. Okay. That function we then can use to help answer the questions. But this function, right, in order to find points where it's maximized, we needed its derivative. So that's why you see here, we took our profit function and we took the derivative of it. That's to go find those critical points. Now, make sure you see here that once we dealt with this, we did find 2 critical points. Okay, I used factored form. I only kept that 5/3 though, because it was positive. This other one gave me -1, and I don't want a negative, so I just kind of ignored it. Okay, so again, it's like if you chose, instead of factoring quadratic formula, just remember, hey, I got a negative here. I'll set that aside. It's there, but that's the algebra. I want the positive because that's what's applying to the situation. Okay. Make sure you read the problem. As you see here, it was in thousands of units. So that's how many units we got. And as you can see, if you just go to the 3rd decimal place, that'll give you to the nearest 1,000. To the nearest whole amount, sorry. Then make sure you see, though, when I plugged it back in one last time, I plugged it back into the profit function, not its derivative. The derivative helped us find the 5/3. I'm good with the derivative now. This needs to get plugged into the profit function to find, hey, what is the maximum profit, which we see here, the $5,481. Any questions before we go on to the next one? All right, so I have another one here that kind of follows what we just looked at, but it's a little bit more detailed for a specific situation. All right, once it's to maximize the profit, again, it says that you have Rags Ltd, a clothing firm, determines that in order to sell X amount of suits, the price per suit must be P equal to 150 minus half of X. It is also determined that the total cost of producing X suits is given by the cost function here, C of X equal to 4,000 plus a quarter times X squared, right? So they want us to go through the process now to find the total revenue, find the total profit, and then it's saying how many suits must the company produce and sell to maximize the profit. Then it's going to ask us for the maximum profit. And then lastly, it wants us then to go find the price per suit that must be charged to maximize profit, right? So you'll see here, this is kind of the little extra piece this time, but that goes back to the fact that this is not the revenue function, right? So keep that in mind. That's not the revenue function. Before it gave me the revenue function, but now it wants me to find one. So how do we find a revenue function when it doesn't give me one? Well, if this is going to set the price that you are going to be selling the suits for, well, then all you need to determine is how many suits that you sold at that price. So make sure you see here, if you're given a price function, the revenue function then will always be X times whatever the price function is. I know they don't put a P of X, they just put P because they don't want you to think it's profit, it's the price. So make sure though, if you forget that, just kind of reason out to yourself like, hey, if I sell 100 suits, well, whatever the cost is, it's 100 times that. So that's where I'm coming from with this. The number of suits we're selling times the price of each suit will give me my revenue. And so what you'll find is this revenue function here will simplify down to 150x minus 0.5 x squared. Similar to the price function, right? But remember, we distributed the x through. So any questions with that? All right, so now give myself a little space. Hopefully you have a copy of that or something. What I'm going to do right now is shrink this down some. So I found that first piece it wanted me to, was go find the revenue function. Now remember the next piece that it wants me to find is the profit. Right, so find the total profit. Now make sure you remember, as we just talked about, the total profit is the revenue minus the cost. So we have the 150x minus 0.5x squared. And what we want to do now is subtract the cost from that. But just make sure, as I stated before, put it in parentheses. Once you get to here, the key is to see that both signs change when we look at that cost function. When you do the subtraction, all the signs should change in the cost function. So they were both positive, now they're both negative. But you'll go into this situation though where, hey, I just got to combine like terms. So we get what, 0.75 x squared plus 150x minus the 4,000. The only like term we had here was our x squared term. All right. Any questions or concerns where I'm getting the profit from? The total profit, sorry. Now make sure as you're dealing with these, always read that word right, because we had some of those situations where we talk about like average instead of total. right? So make sure you're always reading that. We want the total profits. That's what's telling me, hey, just take the total revenue, total costs, and do the subtraction. Okay. Now, with that said, we've worked on two parts of this, and they want us now to find how many suits must the company produce and sell in order to maximize the profit. Well, as we talked about before, let's just jump in and do the derivative. So I'm going over here, looking for how I can maximize the profit. So this will give us 1.5x plus 150, which is actually kind of nice. Make sure you see here the 4,000 a constant term, so it's gone to 0. This is a linear term, so that's why just the x dropped off. But 0.75 times 2 is where I'm getting the 1.5 from. The reason I say it's nice, though, is because when you go set this equal to 0, 1.5 works nicely with the 150. Trying to see if I messed up my sign somewhere, y'all.
It should be negative 0.75x squared.
Yep, I totally dropped my negative, huh? Thank you. About to say, this doesn't, we want a positive number, not a negative number. Thank you. So I dropped my negative here. These were both negative, and I made it a positive. It should have been negative. Sorry, y'all. So when we go to our derivative, now the reason I caught that again, though, remember, as I stated on the previous problem, we ignored the -1 here, right? Because we don't want negatives right now. So that was my alert that I dropped something somewhere that, hey, this better come out positive. Otherwise, I'm not going to be able to answer the problem it wants me to. But as mentioned, these were both negative, so I should have kept my negative here. So sorry about that. So when you do the division, though, you should get 100. Just make sure you remember, though, that 100 is coming from the idea that we're saying that's the total number of suits that the company must produce, right? So the company wants to produce 100 suits. Okay. Now, with that said, again, if you do the second derivative, you'll get a negative number. So this is definitely the maximum value, right? To get to the maximum profit, though, so we got the number of suits now. Just remember, though, to get to the maximum profit, we got to plug this back in to the original profit, total profit function that we had. Okay. Any questions with getting to the value that I have here, though, after I made my little mistake with signs? All right, then. So the next step, as mentioned, though, we want to take the 100 and say, hey, what is P of 100? So get your calculators out. Make sure we're comfortable with that. Make sure you fixed it to negative 0.75 as well. All right, so when I plug 100 into this equation, I'm going to get 3,500. Now, keep in mind what that means to me, though, is my maximum profit that we're looking at here. That's 3,500. So like when we go over here and say maximum profit, we would say, hey, the maximum profit is 3,000 500. The company had to produce 100 suits to get there. Right? But that will be our maximum profit. Now, if you remember though, as far as just kind of like our first derivative test, what we're seeing is this is a quadratic, right? That's going to look something like this. We're looking at this particular point. That's where we're focused on. Over on the left here, the profit's increasing to that point, right? So it won't be 3,500, but we know it's growing to that. Once I get here, though, if I keep producing suits, the profit's going to start dropping, right? So this is why we want to find this point. Where's that nice middle ground between the costs and the revenue? Now, this last one, what they want you to do, though, so now that we got that one, for this last one, it says what price per suit must be charged in order to maximize profit. That goes back and said, hey, don't forget you started with this price function. So we're going to go up here and say, hey, P equals 150 minus 0.5 times the 100, which will give us 100. So we need to charge $100 per suit. So whenever you get here, just make sure you're going back and saying, hey, what am I supposed to use? Because this one here wanted us to maximize profit. So that's why we were focused on our P of X. That's why I plugged into P of X, right? Was to get to that profit piece. Here they said, what is the price per suit? So that's where we go back up to the beginning and said, hey, the price per suit was given to me here. So if I plug 100 in for X here, as you see I did, that'll give us the price, okay? And that will allow us to then to identify the price that we should be charging for that maximum profit. And that'll allow us to say, hey, I got all the pieces I needed here. We're good to go. So are there any questions or concerns with this one I can help clear up for somebody? All right, just to summarize then, make sure you see here we were talking about, total profit again. Just make sure you see the difference between this one and the previous one is here I gave you both the revenue and cost functions, where sometimes you're not going to be given both of them, okay? Now, if I had time, I had a minimizing cost one, but I think that's where we're going to pick up. We'll look at some stuff that's like dealing with minimizing. So here I did have a minimizing example, and we'll deal with that on Wednesday, just to make sure we have a different perspective there as well. Okay, so our right now focus is maximizing profits, but minimizing costs is definitely something else we want to look at too. Okay, but as you look at this problem here, make sure you see that the total revenue came from us knowing the price that we're going to charge. Just remember that, hey, whatever price you charge, the number of suits that you sell at that price will give you the total revenue. That's where I came from this. It's, hey, the number of suits I produced times this price here, that's my total revenue. Profit, as we talked about, comes from that subtraction, right? Subtract the total cost from the total revenue. And anytime you're asked to maximize or minimize something, make sure you get to that function and you use the first derivative. Okay? Those critical points will help us find those minimum and maximum values. Now, like as I mentioned, the second derivative is helpful, but as you'll see here, it would have been just negative 1.5, which would have just, hey, it's always concave down. So this is definitely the maximum value we want after 100. Okay. I definitely want to kind of make sure we get it clear though, as we go to this next test, it's probably going to be a more application focused than the previous tests have been. So keep that in mind as you're going through this and taking notes of all these different problems that I can give you, because there's different ways that we've been able to talk about, especially from other sections too. We're able to start adding to what we're doing. Okay. Are there any questions or concerns though before we finish up today? All right, for those of you who jumped in that after we started, please make sure you get your first and last name into the chat for me. If you don't have any further questions, though, have a good day, and I'll see you all on Wednesday.